Good morning, welcome to new lecture. Today I will talk about shear strength and Poisson ratio. In this lecture, I will go through what is the shear strength and how we will calculate shear strength, and then I will define Poisson ratio. What is the Poisson's ratio and how we can calculate Poisson ratios. Let's start with shear strength. Assume we have block of material. So assume one block of soft material. This block of soft material, assume the material property is rubber. So if I show this in 2 dimensions, will be like this, and assume this length, it is A, this side it is B, height it is H. So we have block of material, material property it is rubber, it is soft material. I stick this material to 2 steel plate, something like this. So these are 2 steel plates, and between those it is one block of soft material. Assume it is from rubber. So if we make this system and then I apply force like this, one force for example in this direction here, another force in this direction. So it is couple force, magnitude equal and opposite direction. Magnitude, for example, this F, this is F, this is rectangular, and this side it is A. It is block, the side perpendicular to the board it is B, the length it is A, the height it is H. If this system is subjected to this couple force, what will happen? This is first rectangular shape, so we will have deformation. After deformation, that will be similar to the parallelogram, something like this. So the shape will change and it will deform. Initially it is rectangular shape, then it will be parallelogram. If we assume a small element here and a square shape element, force this F divided by cross-sectional area which is tangent to that cross-sectional area. This cross-sectional area it is A times, here in this example, cross-sectional area it is A times B. This force it is tangent to that cross-sectional area. Force divided by that area, it will create stress which is tangent to that surface. We call it shear stress, and we will show with Greek letter tau. Tau it is shear stress. It will be force divided by area. Which area? That area force is tangent to that area. In normal stress, force it was perpendicular to that area. And if we look up to this top view of this is B, this is A. Top view, this stress will be tangent to this surface. Of course, distribution will not be uniform and will depend on the shape of this cross section which is tangent to that, but assume average one it is. uniform. The average magnitude we will show with tau. It is total force divided by cross-sectional area. This is shear stress. This is tau. Normal stress, in normal stress, we had side view of this. This was A. The B part is perpendicular to the board. It was perpendicular to this section. So this is normal stress. Normal stress, sigma, is perpendicular to cross section. Shear stress, tau, it is tangent to this surface. You see what is the difference? If I look at to this small element, I draw that element bigger. This is a small differential element. Here I will have shear stress tau, which is force divided by area. In order to have this element in equilibrium, I will have another tau here. So if I write summation of now stress or summation of force, stress times the area of this element in the horizontal direction, they will cancel each other. So summation of forces in x direction equal to 0. So tau times the area which is tangent to this area in horizontal direction will be from, this tau will be from left to right. We need another tau from right to left. The magnitude should be equal and they will cancel each other. Now this element, it is not in equilibrium. It can rotate respect to the center and it can rotate clockwise. In order to fix it in one point and make that rotation 0, this tau will create shear stress in vertical direction as well. Now, in this element, summation of forces in horizontal direction is equal to 0, so they will cancel each other in horizontal direction. Summation of forces in vertical direction is equal to 0. They will cancel each other in vertical direction, one of them upward, another downward. Summation of moment, for example, respect to the center point is equal to 0. Again, they will create equal and inverse moment in opposite direction. One of them it is clockwise. For example, this tau and this tau wants to rotate this element clockwise. This tau and this tau, they tries to rotate counterclockwise. Because the magnitude is equal, they will cancel each other and this element will remain in equilibrium. So in one element, now we see the stress, shear stress. But we will have deformation. First, this block, it is rectangular shape. You see in 2 dimensions, it is rectangular shape. After we apply these forces, it will deform. It is easy to understand. It will deform and it will be parallelogram. So this element will deform to this element. Initially it is a square shape. Now it is a parallelogram as well. So what is happening here? If we look at to that element, if I draw that element a little bit bigger, see what is happening here. Initially it is a square shape. Then after deformation, it will be like this blue parallelogram. So what we have here? We have here this deformation in, if this is x direction, I show this deformation delta x, and this will be delta x as well. And the height it is 8. So if this angle is beta, if this angle is beta, tangent beta will be equal to delta x divided by h. Pay attention, our material it is linear elastic and deformation is very small. If deformation is big, material, they are not in linear elastic range. In mechanics of material, we assume our material behavior, it is linear elastic and it obeys Hooke's law, and all stress, it is below the proportional limit. So this deformation, it will be very small, that delta x. If delta x is small, delta x divided by h, it will be small number. So tangent beta, it will be very small, and beta, it will be very smaller than 1. So for small angles, if I show tangent beta with gamma, gamma will be equal to tangent beta, and that roughly will be equal to angle in radians. So it will be equal to angle in radians. So I can show with gamma, because gamma tangent is equal to the tangent beta, and tangent beta, because it is a small angle, is equal to the beta in unit of radians. From here I can write gamma is equal to, instead of tangent beta, I can write gamma is equal to delta x divided by h. This we call it shear strain. This gamma we will call it shear strain. So if I want to define it from what we saw, what is the gamma? Gamma, or shear strain, is defined as the change in right angle and it is measured in radians. So gamma we call it shear strain. The definition, it is shear strain. You see, it is change of right angle. Here initially this element angle was right angle. It was equal to pi over 2 or 90 degrees. Change in that angle we will show with gamma. So after deformation, this is gamma, and we will call it shear strain. So shear strain is defined as a change in right angle. This part we call it gamma or shear strain. And you see what is the difference in shear strain and strain. Let's, if I remove these. This is initial shape of element, then it will deform like this angle gamma, we will call it shear strain. And here we have shear stress. In normal stress, if it was our element, after deformation, it will deform like this dashed line. In the lateral direction, it will get thinner. In the axial direction, if we have axial normal stress, in the axial direction, it will elongate, it will get bigger, longer, and in the lateral direction, it will get thinner and smaller. So this was deformation divided by initial length, we call it strain. This is this deformation divided by height, or tends in right angle, we call it shear strain. Now, if we conduct one test for one material, for example, if we come back to initial example, we have that block, and that block from one material of that block, it is linear elastic material. We attach to the rigid plate and we apply force F and F. We can calculate shear stress. It will be force divided by cross-sectional area. This cross-sectional area is the area this load is tangent to that area. And we can calculate the gamma. Gamma will be deformation divided by this height. For example, I show again here at I can calculate gamma as well. If I show stress strain curve here, vertical axis it is shear stress, horizontal axis it is shear strain. For linear elastic material in linear range, in small deformation range, the curve will be again linear. And if this angle is alpha, here again tangent alpha will be equal to one constant like capital G. Capital G, in the normal stress we had capital E, we call it Young modulus. Here capital G, it is again the same property, it is shear modulus. So capital G, it is shear modulus. Over there we call it Young modulus, we show with capital E. Here we show with capital G, we will call it shear modulus. There is relationship between E and G. Later on we will prove that. For now it is good to know the range for shear modulus. Shear modulus usually is bigger than Young modulus divided by 3, and it is smaller than Young modulus divided by 2. So E is Young modulus. We find E using stress strain test, tensile stress strain test. Usually we can find E Young modulus, for example, for steel in tension. G shear modulus variation, it varies from E over 3 to E over 2. It is in this range. greater than E over 3, smaller than E over 2 for most real engineering material, for most of those. I will explain later on more. If you remember, we defined in normal stress and strain, Hooke's law was normal stress sigma is equal to E, Young modulus, epsilon strain. That was Hooke's law. Here again, we can define Hooke's law. Hooke's law here, it will be tau equal to G shear modulus times gamma. Gamma, it is shear strain. So look at to Hooke's law. If we have one rod, we apply tension for linear elastic material in small deformation range. The curve is like this, and Hooke's law, it is sigma is equal to E epsilon. If we have rod, we apply tension or compression like this. If we have material and we apply shear force like this, here deformation, it will be elongation. Here deformation, it will be like this. If we draw stress-strain curve, shear stress, shear strain curve, shear strain here, sorry, it will be gamma, not epsilon, gamma. For linear elastic material in a small deformation range, this slope this time will be G, and Hooke's law will be tau is equal to G gamma. Tau shear stress is equal to shear modulus times gamma shear strain. And I defined what was shear strain, and you should know G for most real engineering material, it varies in this range. Now let's look at to another term. We call it Poisson's ratio. What is the Poisson's ratio? Poisson's ratio, they name it after a French mathematician, Poisson, because first he found this material property, and for that reason they call it Poisson's ratio. He was French mathematician. If we have one, for example, rubber band, we have one rubber band or rubber strip. If we pull this rubber band, if we apply tension, if we pull this, what will happen? It will elongate in the axial direction. It will elongate in axial direction. So if initially length is L, that length will increase from both sides. For example, delta x over 2 from this side and delta x over 2 from other side. So if we have one material, linear elastic material like rubber band, and we apply tension, we pull it, it will elongate in axial or longitudinal direction. But in the same time, it will contract in the lateral direction. So the shape will be something like this. In the lateral direction, it becomes thinner. In the lateral direction, it gets smaller, it becomes thinner. In the axial or longitudinal direction, it will be longer. So this property shows Poisson ratio. What is the Poisson ratio? Poisson ratio in most mechanics of material, they show with Greek letter nu, or sometimes in old textbook they show with mu. In some textbook you will see with nu. In other textbook, old textbook, they show with mu. You can see both of them. I will here in this course I will show with nu. Poisson ratio is negative lateral strain divided by axial strain. If this is x direction, this is y direction. If I apply tension, this rubber band will elongate in longitudinal or axial direction. So I can calculate positive strain, tensile strain, it is positive strain, which is deformation in axial direction divided by initial length. In the lateral direction, it gets smaller, it becomes thinner. So in the lateral direction, y direction, for 2D member, in plane member, for 2D I don't show the z, but even in the z direction it is the same behavior. It will be strain, deformation in the lateral direction from each side. It is delta y over 2, delta y over 2. So total deformation, it is delta y. If the thickness I show with b, it will be delta y over b. This will be tensile strain. Tensile strain always we show with positive, because it gets bigger in that direction, it elongates in that direction. This will be compressive strain, because it gets smaller, thinner in that direction. Compressive strain we will show with negative. So Poisson ratio, because this is negative for this case and this is positive, negative times negative, Poisson ratio will be always here lateral divided by axial. For real engineering material will be positive number always. Of course for some material it is negative, I will explain those later too, but most engineering real material like steel, like concrete, like plastic, it is different of course. Plastic, those kind we are using in civil mechanical engineering, most of the time it is positive number. Anyway, that is the reason we have negative here, because this is compressive strain, this is automatically negative, this is tensile strain, so this is positive. Negative type, negative, it will be create positive. This is the definition of the Poisson. Poisson ratio is lateral strain divided by axial strain. Lateral strain divided by axial strain. So I can write even here negative lateral strain divided by axial strain. This is Poisson ratio. If we apply compression, what will happen? If we apply compression, is for example, if it is rod, what will happen? It will contract in the longitudinal or axial direction, and it will expand in the lateral direction. So it will be like this. After deformation, it will be like this. length will decrease in the axial direction, but will increase in the lateral direction. This is usually ordinary engineering material shows this kind of behavior. And as I mentioned, Poisson was French mathematician. Let's write even date here, 1781 to 1840, and he found this Poisson ratio in 1827. For isotropic material, isotropic and elastic material, we know what is the elastic material. I defined the elastic before. Elastic means we apply load, we have deformation. We remove load, we will not have permanent deformation. It will gain initial form. So if we apply load, we will see deformation. We remove load, deformation comes back to the initial shape, and deformation, permanent deformation, is zero. This kind of material, we will call it elastic. Of course, as I mentioned, we have linear elastic and non-linear elastic, and in mechanics of material, we assume our material, they are linear elastic. Anyway, if we have isotropic and elastic material, for those material, theoretical value for Poisson ratio is from -1 to 0.5 for isotropic elastic material. Isotropic means material have the same properties in all directions. So isotropic, let's say, isotropic materials. Isotropic materials means they have same properties in all directions. Or material property, it is independent from direction, in this direction, in this direction, it is the same. So this kind of material, we will call it isotropic material. Theoretical value for Poisson ratio for isotropic elastic material, it is in this range, but for most real engineering material, so for most real material, Poisson ratio, it is greater than 0 and is smaller or equal to 0.5. For most real material, I will tell why we call it most real material. We have in nature or we use in engineering, it is between 0 to 0.5. Let's look at some material Poisson ratio. For most metal Poisson ratio, it is close to 0.3. Depend on the, for example, it is copper, aluminum, steel, it is a little bit different. But for most metal, it is in 0.3 range. So let's look at some material. If you look at the wine bottle, in the top they put cap with cork. Why cork? Because cork Poisson ratio, it is roughly, it is close to the 0. It is roughly, it is close to the 0. It means when it's compressed, there is no lateral deformation. So for cork, if you apply compression, it gets shorter, but lateral deformation, it is close to the zero. So Poisson ratio for cork, it is close to zero. It is zero, roughly. I write like this. For cork, it is zero. For concrete, of course, depend on the concrete type. It is almost 0.2, or I can say from 0.15 to 0.25, on average 0.2 for concrete. For steel, Poisson ratio, roughly it is 0.3, depending on type of the steel and metal. For rubber and incompressible materials, like fluid, like oil, like water, if you put inside of the container, the Poisson ratio, it is 0.5. So the range variation for Poisson ratio for most material, 99% of material you will use it, it is greater than 0, smaller or equal 1.2 or 0.5. So for some material, these material, they are artificial material or created by human or biological material. Some very rare material, Poisson ratio, it is negative. Poisson ratio is negative means, for example, you apply tension, it will elongate in longitudinal direction, but it will get fatter in the lateral direction too. Okay? We have some this kind of material too, like PU foams or like PP fibers and so on. In mechanics of material, we will not deal a lot with these materials. With those materials, we are using a lot. In engineering, Poisson ratio variation, it is in this range. Finally, for isotropic homogeneous material, so let's say right here, for isotropic homogeneous material. What does that mean? For isotropic and homogeneous. Isotropic means material properties same in all direction. So isotropic means the same in all directions. Isotropic means material property is the same in all directions. Homogeneous means material property is the same in all locations. So uniform composition of material we have in entire object, or it is material property is the same in all locations. We call it homogeneous material. Isotropic means the material property is the same in all directions. For isotropic and homogeneous material, we can prove, later on I will prove, G shear modulus is equal to E Young modulus divided by 2 times 1 plus nu. So for isotropic homogeneous material, in mechanics of material we can prove, I will prove later on, G shear modulus is equal to Young modulus divided by 2 times 1 plus nu Poisson ratio. This is very important and you should know as an engineer. G is equal to E divided by 2 times 1 plus nu. Nu here is Poisson ratio. And Poisson ratio was negative lateral strain divided by axial strain. We know nu for most material, it varies from 0 to 0.5. So if we put nu 0, what will happen? G will be equal to, if nu is equal to 0, G will be equal to E over 2. If we put nu, Poisson ratio, 0.5, this will be 1.5. 1.5 times 2, it will be 3. So G will be E over 3. This is the reason I said shear modulus varies from E over 3 to E over 2. For most material, G roughly is equal to 3 over 8 E. So for most real material, G is equal to 3 roughly. 3 over 8 times E. So now today I define you shear stress. You know what is the shear stress? You know what is the shear strain. Shear stress we showed with tau. Shear strain we showed with gamma. And gamma was in unit of radians. So in unit of radians gamma. And tau was shear stress. And Hooke's law, it was here, tau is equal to G times gamma. Before we introduced Hooke's law, sigma is equal to E epsilon. And I defined Poisson ratio and I gave relationship between G and E. For today it is enough. And next session I will start new topic. Thank you so much for watching this lecture. See you next session. Bye bye.